Hydrogen is the most abundant element in the universe. It powers the stars, including our sun, and here on Earth, it holds the potential to power our entire civilization. But there is a fundamental challenge. Hydrogen is almost never found alone. It is a highly social atom, tightly bonded to other elements, most commonly oxygen in water or carbon in natural gas. To use hydrogen as a fuel, we must first break those bonds. In other words, we have to manufacture the universe's simplest element. But here is the catch. Not all hydrogen is created the same way. Depending on how we produce it, hydrogen can either become a major contributor to climate change or one of our most powerful tools to fight it. To track this difference, the energy industry uses a system known as the hydrogen rainbow. Each color represents a different production method and a very different environmental impact. Today we're going on a journey across that rainbow. From the coal-powered methods of the past to the cutting-edge discoveries that may shape the energy systems of the future. Before we explore the different colors of hydrogen, we need to understand one thing. Why hydrogen at all? After all, we already have batteries. Lithium-ion batteries work extremely well for cars, electronics, and small-scale energy storage. But when we scale up to massive systems, batteries begin to reach their limits. Consider a cargo ship crossing the Pacific Ocean, or a steel plant operating around the clock. To power systems of that scale using batteries alone, the batteries would become so heavy that the ship might not even float. This is where hydrogen becomes powerful. Hydrogen is not just an energy source, it is an energy carrier. It allows us to store large amounts of energy in chemical form, while remaining relatively lightweight. If we can produce hydrogen cleanly and efficiently, it could help solve some of the most difficult challenges in the global transition to sustainable energy. Black hydrogen. Black hydrogen is produced from coal through a process called gasification. In this process, coal reacts with high-pressure steam and oxygen at extremely high temperatures. The reaction breaks the carbon-based fuel into a mixture of gases, including hydrogen. The advantage is simple. The process is cheap, well understood, and supported by decades of industrial infrastructure. But the environmental cost is enormous. For every single ton of hydrogen produced from coal, nearly 20 tons of carbon dioxide can be released into the atmosphere. It is one of the most carbon-intensive energy processes ever developed. Brown hydrogen. Brown hydrogen is very similar to black hydrogen. The main difference is the type of coal used. Instead of hard coal, brown hydrogen is produced using lignite, a lower-grade coal with higher moisture content. The process and the environmental impact are largely the same. High emissions, heavy pollution, and a large carbon footprint. Both black and brown hydrogen represent the earliest industrial approaches to hydrogen production. Next comes the current global champion, gray hydrogen. Gray hydrogen is produced from natural gas, primarily methane, through a process known as steam methane reforming, or SMR. In this reaction, methane reacts with high-temperature steam. The molecules break apart, producing hydrogen and carbon dioxide. Today, roughly 95% of the world's hydrogen is produced this way. It is reliable, efficient, and relatively inexpensive, but it still releases large amounts of carbon dioxide directly into the atmosphere. Hydrogen may burn cleanly when used as fuel, but when it is produced through fossil fuels, the factory behind it can still be highly polluting. Blue hydrogen. Blue hydrogen uses the same steam methane reforming process as gray hydrogen, but it adds an additional step, carbon capture and storage, often called CCS. Instead of allowing carbon dioxide to escape into the atmosphere, the gas is captured and compressed. It is then transported and stored deep underground in geological formations. In theory, this dramatically reduces emissions. Blue hydrogen allows us to continue using natural gas while preventing much of the carbon from reaching the atmosphere. However, the system is not perfect. Carbon capture is expensive, and small amounts of methane and carbon dioxide can still escape during extraction and transport. Turquoise hydrogen. Turquoise hydrogen represents a newer and more innovative pathway. Instead of producing carbon dioxide gas, this method uses methane pyrolysis. Methane is heated to extremely high temperatures in the absence of oxygen. The molecule splits into hydrogen gas and solid carbon. This solid carbon, often called carbon black, is a valuable industrial material used in products like tires, batteries, and electronics. The advantage is clear. No carbon dioxide gas is produced, but the challenge lies in the energy required. Methane pyrolysis demands enormous amounts of heat, and large-scale industrial systems are still being developed. Green hydrogen. Green hydrogen is produced through a process called electrolysis. An electrolyzer passes an electric current through water. This splits the water molecule into hydrogen and oxygen. If the electricity used in this process comes from renewable sources like solar, wind, or hydropower, the result is hydrogen produced with virtually zero carbon emissions. The only byproduct is oxygen. It is one of the cleanest energy processes imaginable. But electrolysis requires a large amount of electricity. And as of today, the world does not yet have enough renewable power capacity to replace all fossil-based hydrogen production. Still, green hydrogen is expanding rapidly as renewable energy becomes cheaper and more widespread. Pink hydrogen. Pink hydrogen uses the same electrolysis process as green hydrogen. But instead of renewable electricity, the energy source is nuclear power. Nuclear reactors can operate continuously, providing stable electricity 24 hours a day. This makes hydrogen production more predictable and efficient. However, nuclear energy comes with its own debates. Questions about radioactive waste, safety, and construction costs continue to shape public discussion around this technology. White hydrogen. White hydrogen, also known as geologic hydrogen, is perhaps the most exciting recent discovery. Unlike every other method we've discussed, white hydrogen is not manufactured. It occurs naturally within the Earth's crust. In certain geological environments, water reacts with iron-rich rocks. This chemical reaction slowly generates hydrogen gas underground. For decades, these deposits were largely overlooked. But recent discoveries in places like France, Australia, and North America suggest that natural hydrogen reservoirs could be far more common than previously thought. If these resources can be extracted safely and efficiently, white hydrogen could become one of the cheapest and cleanest energy sources available. However, scientists are still learning how to map these underground systems and extract the gas without leaks. It is a new frontier in energy science. So, which color of hydrogen will power the future? The reality is that there may not be a single winner. The global transition to sustainable energy will likely require a combination of solutions. Green hydrogen may power renewable energy systems. Blue hydrogen may serve as an industrial bridge during the transition. And white hydrogen could become an unexpected breakthrough if natural deposits prove abundant. In many ways, the story of hydrogen is a story about materials, chemistry, and engineering. We already have the element. The challenge now is finding the smartest way to produce it. Because ultimately, how we generate our energy will shape the future of our planet. And that is exactly why matter matters. If you enjoy deep dives into the materials and technologies that build our world, consider subscribing and joining the community.